So I will start to talk about the status of the NEWAGE direction-sensitive dark matter search experiment. So I will start with the very short introduction of the direct dark matter search, because we already have very nice talks from the previous speakers. Various experiments make good efforts to explore the exclusion limit as shown in the right plot. And but we are focusing about the direction sensitive search, and because we are aiming to measure the incoming direction of the dark matter because it tells us the very important information. So the left shows just a picture of the solar system and its velocity, and it always goes to the direction of the Cygnus constellation, and so we will able to detect the so-called WIMP window from the Cygnus. Yeah, so our goal is to make properties to dark matter particles clear. For example, the hypothesis of our hypothesis is true or not, for example. So other goal is to get sensitivity to the neutrino flow region and like that. So as already discussed today. So let's move on to the method to detect the incoming direction of WIMPs. So it is achieved by the detecting the direction, which means the track of record nucleus. So in general, record nucleus tend to have a very low energy and it requires to detect a very such a very low energy. So it is suitable to use a very low pressure gas as a target because of its short track length, as shown in the left plot, which is simulated result of the track length and as a function of the record energy, and when using the CF4 gas with a 0.1 atom. So the track length is the order of only 1 millimeter when using this gas with this configuration. So we need to read out with fine position resolution when using the gas TPC like that. Yeah. So I will move on to the NEWAGE experiment. Yeah, and our detector is placed in the Kamioka mine, which is about 1,000 meters underground. It's nearby Super Kamiokande. It's here. And our laboratory is not shown in the picture, but it's very nearby the Super Kamiokande. Here, very nearby the Super Kamiokande. And the detector, our detector is placed here and like that, and which is mu-TPC, electronics, and gas circulation system. So I will explain more about our detectors. Yeah, we use a gas time projection chamber with microscopic readout system, which is called micro TPC. And the volume is 30 times 40 cubic centimeter, which is filled with CCl4 gas with 17.6 torr pressure. And in order to read out the drift electrons, we use a mu peak, which is 400 micrometer pitch strip readout detector with two-dimensional two dimension. And drift electrons are further amplified by the GEM, which is gas electron multipliers placed in here. And the drift electron goes to the GEM, and it generates the avalanche here, and then mu peak detects the charges. Yeah. So our main background. We have two types of backgrounds, and one is the external background we call, and the dominated external background is gamma, which we call the electron, and this is misidentified to nucleus. But we can reduce this background by analysis because these events tend to have larger track lengths and the dx relative to nuclear recoil events, as shown in the right plot. And this is two-dimensional plots as a function of recoiled energy in the x-axis on the track lengths of the recoiled nucleus or electrons in the y-axis. And black plot is detected using the neutron source, and the blue is gamma source. And so we can see that the neutron source, which is assumed to be signal, is the very short track length, and with comparing to the gamma source. And when we choose a red band, gamma background can be reduced. So another background is coming from the internal detector, the detector in our chambers, which is called the internal background. So it can be reduced by clean detector development, which is a very simple way. So we already developed a new mu peak, which is called low alpha mu peak, and it is installed to reduce alpha source from the its surface. So what is new is that we replaced the surface of the material is to be very clean one, and so as a result, the background source is reduced from the 2 ppm to the 0.01 ppm. Yeah, it's big results. So so using this detector and analysis, we have a very nice energy spectrum, and to achieve succeeded to achieve the ultra low background condition. And so the left plot shows the two runs, which the one using conventional mu peak and in the gray plot, and the black plot shows the one using the new low alpha mu peak. So the background is reduced by the low alpha mu peak as shown in the plot. So yeah, using the latest one, we got the new exclusion limit as shown in the right red line. So this result is from this result we are approaching the Dharma allowed region. Okay, so let's move on to the topic of our recent updates. Yeah, first we are trying to use a lower pressure gas study because low recoil energy events are not taken and due to their short track as shown in the left plot. Yeah, this is also simulated plot as a function of its recoil energy. So we got now current our threshold energy threshold is about 15
2 minutes left to your talk.
Okay, thank you. Yeah, which corresponds to the only 1.2 millimeter drag. So yeah, but the low energy recoil region is more important as shown in this plot. Yeah, we are aiming to use a lower pressure gas, which is equal to low particle density, of course. So first of all, we are trying to use a 16 tall instead of the 76 tall gas with a high gas gain, and we got the test runs. We got this right plot using the test run. So this plot is a distribution with recorded track lengths with the 76 and 16 tolls in a fixed record energy region. So the track length is increased 1.2 times, so it's very successful. Oh no, sorry. Yeah, and from the result, the lowest threshold can be applied, which is 30 keV. So the gain of the event rate, especially for the low mass dark matter region, is very enhanced. But problem is that when we use high gas gain, the background seems to be increased, and we know that the source of the background is gamma. So we have to consider how to reduce the gamma backgrounds. So in order to solve the problems, we prepare the Gamma-veto shield built by Kappa, and it's already installed in our detector to reduce the ambient gamma rays. So gamma rejection is evaluated via session source one, as shown in the right plot, and the blue is without Kappa shield, or red it with Kappa shield. So the background rate is reduced to about 60%. So we achieve the good gamma rejection. Yeah, it is the last slide. I will talk about the feature update. So the development of a modulated chambers, which is very large size, 1.3 cubic meter, is ongoing. Like that. And the chamber is already prepared in the Kobe University here. So the first integration test, which the detector of our readout system is installed in the integration test. It will be taken place next spring, and we also planning to install this large chamber in the Kamioka mine in the next September. Yeah, let me summarize my talk. The direction-sensitive search plays an important role to make properties of dark matter particles clear, and we could reach the Lutonia floor region using the direction information. So NEWAGE experiment is approaching to the Dama Road region, and we already have various updates as discussed now. So we are trying to make the new results as soon as possible. Yeah, thank you.